Hello, let's take a look at the proof of Proposition 3. Proposition 3 says if a line intersects a plane not containing the line, then the intersection of the line and the plane is exactly 1 point. Now remember, we're going to use just the postulates that we have above, and this one, like the last proposition, actually only uses one of the postulates. Okay, so perhaps we should remind you what the postulates are so far. Let's go to the appendix. Here are the postulates. The collection of all points in our geometry forms a set. Lines and planes are geometric figures, which are sets of points. We're going to use those two without really referencing them. So postulate 3 says there exist at least 4 non-collinear, non-coplanar points. Every plane contains at least 3 non-collinear points, is postulate 4. Every line contains at least 2 points, is postulate 5. Postulate 6 says given any two distinct non-antipodal points, there exists exactly one line that contains both of them. That non-antipodal part will be actually added a little bit later. For now, you can just say given any two distinct points, there exists exactly one line that contains both of them. Postulate 7, given any 3 distinct non-collinear points, there exists exactly one plane containing them. Postulate 8 says if 2 points lie in a plane, then the line containing them lies in the plane. And postulate 9 says if 2 planes intersect, then their intersection is a line. So let's get back to where we were. And here's our proof of Proposition 2. You can use that as a model. Okay? So using that as a model, see if you can write a proof of this yourself. Really, do it yourself. Give it a try, and then come back after you've given it a shot. Press pause now. All right, well, you're back, so let's take a look at this. One way to state this is this. Proposition 3, given a plane P and a line L such that L is not in P. In other words, L is not a subset of P. But the intersection of L and P is non-empty. Prove the intersection of L and P consists of exactly 1 point. And again, we're going to do it a proof by contradiction. And again, we only really use one postulate. This time it's postulate 8. If 2 points lie in a plane, then any line containing them lies in the plane. So let's see how we put this together. The given hypothesis is we have a plane P and a line L such that L is not in P and the intersection of L and P is not empty. The reason, given hypothesis. The last step, the reason is, the statement or conclusion we have is that L intersect P equals the set A. In other words, the intersection of the line and the plane is exactly 1 point. So, statement 2, there exists a point A in L intersect P. Notice that the reason for that is statement 1. Notice I actually say you have to look back at statement 1 to see that, and of course what the definition of a non-empty intersection means. Now, we're going to do this by contradiction. So our statement we want to contradict is suppose there exists a point B not equal to A with B in the intersection of L and P. That's a supposition for later contradiction. So any line containing A and B is in the plane P. Okay, and that is postulate 8 along with 2 and 3. So 2 and 3 say both A and B are in the line and in the plane. And postulate 8 says if any 2 points lie in the plane, then any line containing them also lies in the plane. Okay. But wait a minute, that means, what do we got? So now we've got our contradiction. Statement 4 contradicts statement 1. That's the reason for our last step. Look at what we've got. Statement 1 says L is not in P, and statement 4 says any line containing A and B, including L, is in P. And we'll just put that for emphasis. Okay, So what does that mean? Then our supposition must be false, right? What does our supposition say? Suppose there's a second point that's in there. Well, if there's not a second point in there in that intersection, but A is in there, then A is the only intersection point. So we only use postulate 8 as a reason here. So any geometry that has postulate 8 is true will have proposition 3 true as well. Now, here's proposition 4. You might take a look at it before coming back for the proof in the next video. Given a line, a point, not a line, there exists exactly one plane containing the given point and line.